Welcome to Uni Entry TMUA preparation. So every day I'll be posting one challenging TMUA question with a full work solution and explaining all the core methods, where all these core methods have appeared before on previous TMUA questions. I'm also building question banks for TMUA paper 1 and 2, and they will be ready in approximately 3 weeks. The first 100 students who follow my channel, like a post and comment or share will get a free pass for this TMUA cycle up to the exam in October 2026. There'll be approximately 500 TMUA style new questions with new papers and questions added each week. So the materials are created by me, Nicky Grant. I've got 3 Cambridge economics degrees, over 12 years experience lecturing at leading universities, and I've supported many Oxbridge economic applicants with their TMUA prep and interview preparation with a good track record. So for more information, please see my website. Right, so this question asks, for how many values of C does fx equal C have 3 distinct solutions? So in this question, we do not need to specifically find these solutions, but apply reasoning, where it's often best to rough out a graph to help visualize this problem first. The key here is to focus on the words exactly and distinct. That means we are counting how many horizontal levels y equals C, so any arbitrary horizontal line, does it meet the graph f of x in exactly 3 different places. The 4 roots are immediate, x equals 1, 3, 5 and 7. At any of these points, y must equal 0, so this is where the curve cuts the x-axis, as there are no repeated roots in this polynomial. Now check the behaviour as we approach the limit. As x tends to plus infinity, all 4 factors are positive, and as x grows, it grows overall, so the product grows to infinity on the right. Likewise to the left. As x goes to minus infinity, all 4 factors are negative, so their product is positive, and as these all diverge to minus infinity, the graph y must grow up to plus infinity, because it's getting bigger and bigger. Now look between the first 2 roots. If x is between 1 and 3, then x minus 1 is positive, while the remaining 3 terms are negative, and we know 1 positive multiplied by 3 negative gives a negative product. So the graph is beneath the x-axis between 1 and 3. The rest follows the same logic. Between 3 and 5, 2 factors are positive and 2 are negative, so the product is positive. Between 5 and 7, 3 are positive and 1 is negative, so the product is negative. The sign flips again. And then from 7 onwards, as we saw above, as x grows higher, all 4 products times together grow bigger, and it's positive and growing on the right. So that gives us this basic W-type shape. There's one turning point between each neighbouring pair of roots, so this is crucial. So if you would like me to do a video on this, then let me know in the comments as to why there must be only one turning point between each distinct root. From the sign changes alone, we know there are 2 lower dips and 1 upper trough, but we do not yet know whether these minimum values are the same, so this is going to be crucial for this problem. If the 2 minima were not equal, then there would be 1 value of C cutting 3 times where the horizontal line is tangent to the central maximum level, the upper trough, and 1 where it's tangent to the higher of the 2 minima, and we can see this in the graph. And just do this yourselves by drawing 2 W-type shapes where 2 have the same bottom value and 2 have different values, and we can see that only in the case when the 2 minimum values are the same can there only be 1 place where a horizontal line will cut the graph 3 times. So the problem reduces to one question. Are the 2 lower minimum values equal or not? The roots give away the structure. So we can see the roots are symmetrical around 4. 1 and 7 are equally far from 4, and 3 and 5 are also equally far from 4. So substitute x equals 4 plus u into f of x to get f of u. This is just the same graph shifted back by 4 horizontally. So this will not change how many times any horizontal line cuts the graph. It will only change where it cuts the graph. But where it cuts the graph is not relevant for answering this question. Now slot 4 plus u into each factor. X minus 1 becomes u plus 3, x minus 3 becomes u plus 1, and so on. The other 2 factors become u plus 1 and u minus 3. So the shifted function is fu of fu is u plus 3 times u plus 1 times u minus 1 times u plus 3. Now you should see what's gone on here now. Now we compare the opposite factors. U plus 3 times u minus 3 gives u squared minus 9, and u plus 1 times u minus 1 gives u squared minus 1, the difference of two squares. Expanding out gives u to the fourth minus 10u plus 10u squared plus 9. So the important part here is not the expansion itself. The important part is that only even powers of u appear. Replacing u by minus u does not change the value of the function. So we have f of u equals f of minus u for all u. So this is just reflection symmetry in the y-axis. It's also known as an even function. A simpler example is just x minus 4 squared. If we do the same substitution here, 4 plus u, it shifts the graph back where now it's tangent at the x equals 0. It's now reflected around the y-axis. So that means the graph is symmetrical around in our case, u equals 0, which is just the same as x plus 4. So the left and right minimum must have the same value. Because it's symmetrical around the middle, whatever's got the minimum trough on the right must be the exact same value on the left. So we can see here we didn't need to work out what these minimum points were or where they occurred, we just needed to show that they're equal. At the central maximum level, the horizontal line crosses the left outer branch, touches the graph at the middle turning point, it's tangent to it, and crosses the right outer branch. That is 3 distinct real solutions. Any other horizontal line cuts 2 or 4 times. Therefore, there's exactly one real value of c that intersects 3 times, so the correct answer is B. So the key methods you see were quartic polynomials, or just polynomials in general, using roots to build the rough graph, keeping track or looking at the properties of the maximum and minima, and using this even function symmetry to help us determine that the two lower turning points match. So, for the extra challenge, why is it the case for a polynomial with all distinct roots, in between each root there must be one and only one turning point? So if you'd like me to do a video on this, please let me know.